I was in a coffee shop this morning, and I couldn't help but overhear this guy on a phone call.
Oh, yeah.
And he did that thing we all do. He pauses for a long second, lets out this heavy sigh, and then says, "Yeah, the new project is fine."
Ah, the dreaded pause before the fine. That is never, ever good news.
Never. And right away, I knew, and the person on the other end of the line knew, that this project is absolutely not fine.
It's a disaster.
It's probably a total disaster. But here's the thing. I didn't have to stop and, calculate that. My brain just mashed up his tone, that sigh, the pause, and the actual word fine into one single meaning.
And that instant mashup is something your brain does, just effortlessly. It's almost automatic. But for an artificial intelligence, that exact moment is a nightmare.
Because to a computer, the audio wave of the sigh, the text of the word fine, and say the visual of the guy rubbing his temples, those are three completely different streams of data. Right. They don't talk to each other. They kind of live in their own separate worlds. And forcing them to talk to each other, to actually integrate those senses like a human does, that's the holy grail problem we're looking at today.
It's called multimodal fusion.
Exactly.
And we are diving deep into a lecture on this from the MIT Media Lab and MIT EECS given by Paul Yang. It's from a course called How to AI Almost Anything. And honestly, looking through these notes, the how part is just fascinating because it goes so far beyond just, stacking text on top of an image.
Oh, it really does. We're moving from what feels like simple addition to some pretty complex calculus just to teach a computer what sarcasm is.
So let's start with the basics. If I want an AI to understand that phone call I overheard, to process the audio, the text, maybe video all at once, how do I even build that? What's the architecture look like inside the machine?
Well, the lecture breaks this down into a spectrum of three main approaches. And the best way to think about it is probably cooking. The first approach is what we call early fusion.
Think of this as the smoothie method.
So you just throw everything into the blender at the start.
Pretty much. You take the raw audio waves, the raw pixels from the video, the raw text, and you concatenate them. That basically just means you stick them all together into one giant vector.
One long string of data.
One long string of data before the AI has even really processed what any of it is.
That sounds messy. Text is words, video is pixels. How does a machine make sense of that jumble right out of the gate?
It can be very messy, yes.
Yeah.
The advantage is that it lets the model find these really low-level connections right away. Like it might notice a specific sharp shape in the audio wave always happens when a certain pixel lights up. But you're right to be skeptical. The data types are so different, the model often gets confused. It's hard to blend a pixel with a vowel.
Okay, so if the smoothie is too chaotic, what's next? I'm guessing there's a more organized way.
There is. It's called late fusion. And this is
Right.
more the committee approach.
A committee.
Yeah, and instead of a blender, you build three separate, highly specialized expert models. One expert only looks at the face, another one only reads the transcript, a third one only analyzes the audio pitch.
And they don't talk to each other during the process.
Not at all. Not until the very end. They act independently, go off to their separate rooms, do their analysis, and then they come back with a vote.
So the text expert says, I think this is a positive statement. And the audio expert says, I think this is negative. And then you just average their votes.
You just average the votes.
But wait, that seems like it has a huge, huge flaw. If the text is, great job, but the voice is dripping with sarcasm.
Right.
The text expert votes happy, the audio expert votes angry, and the average is just neutral.
Exactly. You get this lukewarm mush. You completely miss the interaction because you've isolated the senses. The magic of human perception only happens when those senses collide and influence each other.
Which brings us to the Goldilocks zone.
Which brings us to deep fusion.
And this is where the layers actually talk to each other during the process, right?
Yeah. Yes. This is also called intermediate fusion. You let the audio representation influence how the image is being processed, and vice versa, all the way through the neural network.
Yeah.
It's not just A plus B.
It's A interacting with B.
That's it.
And that distinction interacting versus just adding, that really is the core theme of this entire lecture. And there's this one case study in the notes that illustrates it perfectly. The case of the smiling critic.
Oh, this is such a great example. It really highlights why that committee approach, late fusion, it just falls apart with complex human behavior.
So lay this out for us. It was a study on book reviews, correct?
That's right. The researchers wanted to predict the audience score. Did people like this book? And they were using video reviews. So they had two main variables they were looking at.
Okay.
Variable A was smiling. How much is the reviewer smiling? And variable B was professional status. Is this a regular reader or a professional critic?
All right, just thinking intuitively. If I see someone smiling while they talk about a book, I assume they liked it. Smiling equals happy. Happy equals a good review.
And for regular people, the non-critics,
Right.
that intuition was spot on.
Yeah.
A positive correlation. A normal reader smiles, they like the book. It's simple.
But
But when they looked at the data for professional critics, the whole pattern just it completely broke.
why? Because critics are just grumpy.
Because critics are complex. The data show that when a professional critic smiled, it didn't mean they liked the book. In fact, it often meant they were mocking it. They were being sarcastic. They were enjoying the process of just tearing it apart.
The shark smile. I know that thing.
Exactly. Now, go back to our committee model, that late fusion.
Right.
If you use that, the AI would fail spectacularly.
Right.
It would see a smile, and the smile expert would add positive points. It would see a critic, maybe add some credibility points. It would just sum them up and say, wow, they love this book.
When the reality is the exact opposite. Right. So how do you do that mathematically? How do you teach an AI that smile plus critic can actually equal negative? How do you code that context flip?
You have to stop adding,
Well.
and you have to start multiplying. This is the core idea of interaction effects. In the regression model, you don't just have a weight for smiling and a weight for being a critic. You add a new term, which is the smiling variable times the critic variable.
So you literally multiply the inputs together.
You do. And in this study, the weight, the importance of that interaction term was a massive negative number. It was negative 2.94.
Whoa. So that single multiplication just flips the whole script.
Precisely. It tells the AI, look, if critic is true and the smile is true, you need to subtract a huge amount of points. It captures the nuance. The meaning of the smile depends entirely on who is doing the smiling.
So context changes content. You can't just sum things up. You have to see how they distort each other.
That is the key. And once you get that simple multiplication explains the smiling critic, well, you can start to understand how we tackle the ultimate boss fight of AI, sarcasm.
Sarcasm is basically just a really complex version of the smiling critic, isn't it?
It is.
You're saying one thing, but meaning the opposite, based on how you say it.
It is. The lecture slides have this perfect example from a video clip. The speaker says, "It's just a privilege to watch your mind at work."
Which, on paper, is a lovely compliment.
A very nice compliment, yes. If you only read the text, that's a positive sentiment. But in the video, the speaker does this huge eye roll and uses this dragging, heavy tone of voice. It's just a privilege.
Okay, so we need a model that doesn't just look at the word privilege and the video of the eye roll separately. It has to capture the collision of those two things.
And to do that, researchers use something called tensor fusion.
Tensor always sounds like something from a sci-fi movie. It sounds expensive. What is it actually doing?
Think of it as brute force multiplication. We just saw how multiplying smile times critic worked for two variables. Tensor fusion takes that to the absolute extreme.
How so?
It takes every single feature of the text and multiplies it by every single feature of the video and the audio.
Wait, every single feature. We're talking about maybe thousands of data points for an image.
Easily.
Yeah.
Imagine a giant grid like a spreadsheet.
Right.
On one axis, you have every single word. On the other axis, you have every visual cue, the eye movement, head tilt, lip shape. Tensor fusion calculates the intersection of every single pair.
So it checks privilege plus eye roll, then privilege plus head tilt, then mind plus eye roll. It checks every possible combination.
Every single one. That's called the outer product.
Yeah.
It creates this massive 3D grid, and that grid captures the eye roll, interacting specifically with the word privilege. That one intersection, that's where the sarcasm lives.
That sounds incredibly thorough, but also wildly inefficient. I mean, if you have 1,000 data points for text and 1,000 for video, you suddenly have 1,000,000 interactions to calculate.
It explodes computationally. You hit the nail on the head. That is the huge downside of tensor fusion. It creates these massive mathematical objects that are just incredibly slow to process.
So we can't exactly run that on a smartphone to detect if my friend's text message was sarcastic.
Not easily, no. And that's why the lecture then talks about something called low-rank approximation.
Translate that for us.
It's basically a mathematical shortcut, a clever math trick. Researchers found ways to estimate what's in that giant grid without actually calculating every single cell. You compress the data.
So you keep the insight, the sarcasm detection, but you ditch most of the heavy lifting.
Exactly.
Okay, so we have the brute force method, multiplying everything by everything. But is there a smarter way? I mean, humans don't analyze every pixel against every syllable.
No, we don't. We prioritize. Think about it. If you're on a Zoom call and the audio cuts out or it gets all staticky, what do you do?
I stop listening to the noise and I just stare at their mouth. I try to lip read.
Exactly. You gate your senses. You turn down the reliability of the audio and you turn up your reliance on the video.
Yeah.
AI can do this with something called attention mechanisms or gated fusion.
So the AI literally has a volume knob for each sense.
In a way, yes. It learns these weights dynamically. It learns to say, okay, right now the audio is noisy, so I'm going to set the audio weight to almost 0 and I'm going to trust the video. It learns when to pay attention to what.
And this leads to this really cool visualization in the slides called modality shifting. I really want to dig into this because it changed how I picture AI thinking.
I love this concept. It's such a beautiful way to visualize meaning.
So help me picture it. We usually think of words inside an AI as being sort of fixed, right? The word expectations has a specific code or a vector.
Right. In a standard text model, expectations sits in a specific spot in what we call the vector space, the map of all words. Usually it's a pretty neutral spot.
But the lecture suggests that the tone of voice can physically push that word around on the map.
That's it, exactly. If the voice saying expectations is trembling or sad, the model uses that audio vector to shift the word expectations over towards the sad corner of the map.
So it's not just word plus tone. The tone actually changes the definition of the word just for that moment.
It colors the language. Expectations effectively becomes a sad word. If the voice was bright and happy, it would do a positive shift over towards the happy corner.
That feels surprisingly human. It implies meaning isn't fixed in a dictionary. It's fluid. It moves based on how we say things.
It is sophisticated.
Oh.
But, and there is always a but in AI, even with these really advanced architectures, these models can be incredibly lazy.
The lecture calls this the greedy modality problem, which sounds like a character flaw.
It practically is. You give the AI all this rich data, video, audio, text, and instead of learning the nuance and the interaction, it cheats. It looks for the shortcut.
Give me an example of a cheating AI.
The lecture brings up the kinetics data set. There's a huge collection of video clips of people doing actions, playing soccer, swimming, running. You want the AI to learn to watch the motion, the kicking, the stroke, the stride.
Okay, that makes sense.
But when researchers looked at what the AI was actually doing, they realized, hey, wait a minute. Every time I see a big green field, the answer is soccer.
So it just stops looking at the players.
Completely. It ignores the optical flow, the motion data, which is computationally hard to process, and it just looks at the static background image, which is super easy. It gets greedy for the strongest, simplest signal.
But that's a huge problem if the scene changes. Like if kids are playing soccer on a concrete street or a dirt lot, that lazy AI is going to fail because there's no green grass.
Exactly. It hasn't learned the concept of soccer at all. It's just learned the correlation of green grass.
So how do we force the student to actually study? The lecture mentioned something called gradient blending. Sounds intense.
It's basically a way of forcing the model to learn the leftovers. Think of it as handicapping the cheater.
Handicapping it how?
Well, imagine we first train the model to guess the action only using the image of the grass. It gets it right maybe 80% of the time. It's smug. It thinks it knows everything. Then we train a second part of the model, the part that looks at motion. But we tell it, you don't get points for what the grass already explained. You're not allowed to learn the easy stuff. You only get points for explaining the errors, the 20% that the grass got wrong.
Ah, so it has to look at the motion because the green grass clue can't explain the street soccer game.
Precisely. The residuals, the leftovers. That's where the real nuance is hiding. By forcing the model to focus on the residual, you force it to use every modality. You strip away the shortcut so it has to do the hard work.
That is so smart. It really shows that building good AI isn't just about the architecture. It's about how you discipline the model during training.
Optimization is every bit as important as the design. You can have the smartest brain structure in the world, but if it only wants to take the easy path, it's never going to learn true understanding.
So we've gone from mixing smoothies to multiplying sarcasm to shifting the meaning of words. And finally, catching the AI cheating on its homework.
Yeah.
It's pretty clear that fusion isn't just glue. It's about interaction.
It is. It's the idea that the whole is fundamentally different from the sum of its parts. You can't understand the world by just adding up lists of objects and sounds. You have to understand how they change each other.
Before we wrap up, I want to leave everyone with one final thought from the lecture assignments. It's a bit of a philosophical curveball. The Platonic representation hypothesis.
Oh, the heavy hitter. I love that they included this in what's a very technical course.
It goes back to Plato's cave, right? The idea that we only see shadows on the wall, not the real objects casting them.
Right, and the hypothesis here applies that to AI. It asks this really big question. If an AI gets good enough at fusion, if it can see, hear, read, and sense the world perfectly, will all those different models eventually converge on one true representation of reality?
A representation that exists beyond the senses. Like, the AI doesn't think in images or words anymore, it just thinks in concepts. Catness, sadness.
It suggests that different AI models trained on totally different things, one on YouTube videos, one on books, might eventually arrive at the same internal language to describe the universe. It implies there is some truth out there that these machines are slowly converging on.
Or are they just staring at the green grass and guessing soccer?
That is the question. Are they seeing reality, or are they just seeing better and better correlations?
Something to mull over until our next deep dive. Thank you so much for walking us through the math and the magic of this.
Always a pleasure.
And thank you for listening. We'll see you next time.